So where are we and where are we headed, right? So just very briefly, we've sort of operated in three levels of abstraction. One is normed linear spaces, one is metric spaces, and one is abstract topological spaces, right? Even though our main interest is really in Rn. Okay, and so today what we want to do is really look at a bunch of continuous functions. There are just lots and lots of them, and we can construct them in many ways. This will also, one more thing, we've also seen compactness. This is a crucial notion. So use, and then we proved this key result, which is Heine-Borel theorem. What does that say?
Closed interval AB is compact.
Right, in
R.
In R, okay. But more generally?
Compact set is closed and bounded in R.
A compact set is always closed and bounded only in R?
Rn.
In Rn, but in fact, this result is true in any metric space. What is special about Rn?
Sir, it's if and only if. So
right. So the converse is true in Rn, which is that if I give you any closed and bounded set, then it is compact. Okay, and using this, for example, we saw that a continuous image of a compact set, if I have a continuous map between two metric spaces, then the image of a compact set under this map stays compact. Okay. Anyway, so let's move on, and let's see that there are many different ways of constructing continuous functions. So, okay, and I should also start recording.
Recording in progress.
Okay, so let's just go through a list of ways of getting continuous functions. So before that, we had many different characterizations of continuity. So let's write this down. All right, so somehow this is not cooperating with me. Moment, please. Okay, sorry about that. I had some technical problems. All right, so let's start once again.
Recording in progress.
Okay, so we had various characterizations of continuity of a function between two metric spaces. Let's just quickly recall that. So F between metric spaces continuous various things. So I will say epsilon delta definition. And then I had two other characterizations, right? One was in terms of sequences. Whenever I have a convergent sequence, and if I apply F to that, I get a convergent sequence in the target. And the limit goes to the limit. Means any of the following. And what was the third definition? I mean, third equivalent characterization?
F inverse of an open set is an open set.
Correct. F inverse of open in Y, open in X. All right, so let us see a bunch of functions that are continuous. So examples of and the idea is that we are going to use whichever definition of whichever one of these characterizations is most convenient. So and the first few are really very easy. Any constant function, identity function from X to X, or more generally, inclusion, any subset from S to X. So why are these true? Okay, come on. So this is easy. Which definition is easiest? I mean, some of these are so easy that you really can use multiple definitions. But for example, all 3 bullet points, they can be directly seen by using the topological definition that inverse image of open set is open. For example, why is a constant function continuous?
So because the inverse image is all of the space, so that is open.
Yeah, well, the inverse image of any open set is really going to be either all of the space or
phi
empty, right? Depending on whether the set that you have taken in the target contains this constant pointer. So, etc. Similarly, for the second one, we know that open sets of S are precisely open sets of X intersected with S. But that's exactly what inverse image does. It intersects any set with S. And so on. So there really isn't much to these things. Okay, so now here comes. Let's write it like this. Let us suppose I'm projecting onto any coordinate. So Rn to R, let us say x1 up to xn goes to some xi. Okay, so why is this continuous? Nothing much exciting is going on. Okay, so when we come to some interesting stuff, I will tell you. This is all straightforward stuff. So why is this projection map continuous?
Sorry,
One way is with the
Yeah, go ahead.
one way is with the sequential criterion. We saw that, so we take a sequence in Rn which converges to something. We saw that converges if and only if every slot converges, in the sense we mean for R. And that directly gives it to us from what the sequence is.
All right, so let's write this down. This is also a useful thing, very useful. So I will just write a recall. Sequence in Rn. Let us say Vn bar converges to Vn if and only if Vni converges to Vi for each slot I. Okay, so this is written in a slightly sloppy way. I'm not really explaining the notation, but we've done this before. So you see, this thing about the projection comes automatically out of this. But in fact, more generally, if I have a map, let us say I have a map from R, R3 to R4, which takes let's say X, Y, Z to X, X, Y, Y. For example, is it clear that this map is continuous? How do we see this? Okay, so there is again no mystery about this. So let us say using for example, if I take a sequence on the left hand side, then it is xn, whatever xn, yn, zn, and it converges to x, y, z if and only if the xn's converge to x, and likewise for y's and z's. So if I have such a convergent sequence, then you see on the right hand side, I again use the same definition. I again use the same fact about convergence of points in R4. And this fact just falls out. Is this all right? If there are any questions, as always, please stop. Okay, so why am I saying all of this? Because I get to construct lots and lots of continuous functions by combining these rules. So here's another one. So let us say I have some metric space X. What does it mean to say to give a function from X to Rn? It means I have to tell what happens in each slot. So it will be a sequence of n real valued functions. So we say that f is continuous if and only if each fi is continuous. Okay, so one thing to say, whenever I say continuous, it is understood with respect to what topological structure. The topological structure has to be given. So X is given to be a metric space, and whenever I have Rn, it will always be a metric space with respect to the norm that we have defined, the three equivalent norms, 1, 2, or infinity. And today we will finally see that in fact all norms are equivalent. So with respect to any one of them. Okay, so what is the proof here? I claim that this function is continuous if and only if each one of the fi's is continuous. Why so? Okay, which one of the definitions shall we use here?
So I think the sequential convergence will work.
Right. So the sequential convergence will again work, right? So maybe what I can do is I can number these 2, 3, 4, 5. So using sequences for, so let us say use open sets here, using sequences for 4 and certainly 5. So let us see this once again. Suppose we are asked to write a proof. So what does it mean? The first sentence is, let us suppose that I have a sequence xn that converges to x that converges to some small x in the metric space X. Okay, so why not write this down? So if xn converges to X, and f is continuous, that would mean that f of xn converges to f of x, right? But what does that mean? Remember, f of xn is a sequence in Rn, and such a sequence converging to a point simply means that in each slot, whatever the entry is, that converges to the respective slot of the limit, namely f of x. So what does that mean? That means that fi of xn converges to fi of x for all I. So this proves one direction. How about the converse? So
I think we can just reverse everything.
right, so we just reverse everything. Of course, what we have to say, the xn converges to x, that has to be part of the hypothesis, right? So I'm simply going to say etc. Okay, very good. So you see, it is very easy to construct now continuous functions to Rn. Namely, I just take a bunch of continuous real valued functions on x and string them together. Okay, very well. Nothing much exciting so far. But now, so this is really just recall. I'm not even going to say number 6 here. So this is just recall. What I would like to do is the following. So where are we headed? I want to say that I can do algebra of continuous functions, which is to say, if I have two real valued functions, then their sum and product are continuous. And I can also take the reciprocal of a continuous function as long as I stay away from division by 0. Okay. So the thing is, to do this, I can separate out the f part with the addition or multiplication part. So what I would like to say is that, okay, so maybe we can just say 6. R cross R to R. The functions x comma y going to xy, or x plus or minus y, or xy are continuous. And yet again, we will use sequences. Okay, so I'm going to say 6 even here. But the sequential definition of continuity, if I want to use that to prove that these functions are continuous, then what is it that I need to prove?
I think we need to prove that if a sequence x1, xn and sequence yn converge, then xn plus yn also converges to the sum of the limits.
Correct. Xn plus or minus yn. This sequence converges to x plus or minus y. And the sequence xn yn converges to xy. So this is exactly the bread and butter of stuff that you did in your analysis 1 course, right? This must have been proved at some time in class or in the homework. Do you recall this?
Yes.
Right? Okay. So for example, are both of these completely straightforward?
I think so.
Okay, so let's just think of this a little bit. Suppose I give you an epsilon, right? And you want to find a delta with the requisite property. How do you do it for in the first case, where I'm taking the addition x plus y?
For each of the sequence, you find n capital N such that
Right,
the
sorry.
difference.
Right. So I'm sorry, not delta, but capital N. Yes. So what do? You find capital N such that beyond that,
Difference is less than epsilon by 2.
right. So here it is very easy. You just ensure that xn is within epsilon by 2 of x and yn is within epsilon by 2 of y. And then the sum by means of triangle inequality will fall within epsilon. This is very good. Easy. For minus also, it's really the same thing. Does the same thing work for product?
No, sir.
Yeah. So here there is something extra, right? You have to bound these things. So things of this nature, I expect you to be able to do without difficulty. And if you have some hesitation, then this is just telling you that you should sit down and write this down for yourself. Okay. So recall from analysis 1 and one more thing. Okay, so let me not be lazy here. There was one more thing, which is that so this is my pad. So this is really all in recall. Again, if you want to prove this by using sequences, for example, then you have to do some work, correct? So I leave that for you. But now, putting all of these things together, what do I get to say? So let us say, by the way, so by induction, if I have a function which is from r cross r cross r to r, which is adding 3 things or multiplying 3 things, then that is also continuous, right? Just apply this one by one. First, you go from r cross r cross r to r cross r. And then do the same thing again, if you will. So here's sort of one upshot of this. Sum and product of 2 continuous real valued functions x and so are continuous similarly, and this immediately says that okay, so before we come to therefore, so so suppose I have 2 continuous functions x, let's say f and g from x to r. Why is f plus g continuous? This is just fun and games. It's like straightforward now. So this continuous implies the function x going to r cross r, which is f comma g. So my notation is bad here. F, G, both continuous implies this function x going to f of x comma g of x is continuous. And then I can take plus. This is the addition of two functions. And similarly, I can multiply them, etc. Likewise, is continuous. So this goes to fx plus g of x. Likewise, if f is continuous from x to r, implies 1 over f is also a continuous real valued function. But on what? The function 1 over f is not going to be a function defined on all of x, right?
But from the points where it is vanishing.
Right. So how do I write this? On what set will it be defined?
R minus f inverse 0.
Yeah, so x minus f inverse of 0. Now, what kind of set is this x minus f inverse of 0? I claim this is an open set in X. Why?
Zero is a single point, so it is closed, and inverses of closed sets are also closed sets when f is continuous.
Right. So because, so I will say reason. Closed in okay, but why is the singleton set 0 closed? Is there anything special about 0?
No, any singleton is closed.
Correct. And how do we see this? So
You can't draw a circle around a singleton set. That will also be a part of itself.
okay, so let me write this down. Any singleton set X in fact, the metric space not sure what you're saying over there. How do I show that a set is closed?
Its complement is open.
Okay, so is it clear? Suppose I give you a metric space and I give you one fixed point in that. Let's call that point P. So the complement of P is open. How do I show this?
If you take a point in the complement of P, then you take the distance between that point and P, divide by 2.
And take, so let us take another, let's take some point, some varying point X. Then I just put a ball around X of radius, let's say half the distance between P and X. I can even take the exact distance because it's an open ball. And this shows that the complement of P, singleton P, is open because I have shown it to be a union of balls. And this is our usual go-to method of showing that a set is open. You can also show that a singleton set is closed by considering what its limit points are. Remember closure of a set. The closure of a set consists of all points in the set along with its limit points. And how do I get limit points? Anyway, so you see that the only limit point of a singleton in a metric space is going to be itself, nothing else. Okay. Once again, whatever we are doing over here is really sort of very basic stuff, and it should all be at fingertips. So what's the upshot? So we are saying that if I take two continuous functions or more, then their sum or product is also continuous. So in particular, therefore, any polynomial in continuous real valued functions on X is a continuous functions. How do I do this? Let's sort of see this a little more pedantry. So for example, in item number 4, I have given this map, right? X, Y, Z going to X, X, Y, Y. So from this, I get that the function from R3 to R, which is X, Y, Z going to X square, Y square, is continuous, because I just have to string together the function that I have written over here with the multiplication function from R4 to R, which I have shown to be continuous, right? So each one of the ingredients is very small, but I get a whole host of continuous functions. All right. And by the way, if I take a rational function of continuous functions, then that will also be continuous, but it will be continuous on an open set. Is this clear? The reason is because both the numerator and denominator are continuous functions. So on the set where the denominator is non-zero, I have a continuous function. But the set where a denominator is non-zero is again going to be a closed set, because the denominator is a continuous function. And avoiding the value being 0 means I'm taking the inverse image of 0. 0 is a closed set. So its inverse image is going to be a closed set, etc. Right? Okay. So some special cases of this, really, special cases. Suppose I have, let us say I have two vector spaces. So let's say I have Rn to Rm. And let us say I have a linear map. So this linear map is continuous. So is this clear? Why is the linear map continuous? Come on. Or is this so simple that nobody wants to talk about it? Okay, anyway. So let us say I have, let's say I take this vector x1, up to xn. Okay. Now it is going to go to m coordinates. So this function t is really a sequence of m functions, but each one of the m functions is going to be a homogeneous linear functions. And what did we see? A map to Rm is continuous if and only if the map in each slot, the map giving the real number in each slot is continuous. Okay, so what is the number in the first slot? It is going to be some number of the type a1 x1 plus up to a sorry, an xn, right? And likewise, I'm going to have m such slots. Is the function in the first slot continuous? Well, of course it is. And the reason is because okay, so to be like completely pedantic, how is the function in the first slot made? Well, you first project onto this first slot, and that function is x1. That function is continuous. The constant function a1 is continuous, so their product is continuous. So likewise, all the functions a1, x1, a2, x2 up to an, xn of the starting vector x1 up to xn, they're all continuous functions, real valued. Therefore, their sum is continuous. And the same thing is happening in each slot, etc., etc. Okay. By the way, so if I write the matrix of P with respect to standard basis, how does this matrix look like? Those A's, where are they?
In the first row.
So the question is it going to be the first row or the first column?
First column.
Well,
No, first.
right. So you see, if I write down the vector 1, 0, 0, 0, 0, etc., where is it going to? It is going to go to the vector a1, vector that is a1 in the first slot, and the rest of the slots I have not written. So you see, this is going to be a1 here, a2 here, up to a n here. And one way to remember this is, what are the dimensions of this matrix? If I have a linear map from Rn to Rm, then how many rows and columns does the
M
corresponding?
cross N, sir.
Yeah, so this is going to be an M cross N matrix. That means it has n columns. Therefore, the number of entries in any row is going to be n. Okay, we are going to need linear algebra pretty soon. Okay, so it's, if you are sort of rusty with it, then it's time to revise that. Okay, so this is a continuous map. Now here is another thing. Let us say I have the space of all. So m n by n r. So these are square matrices, right? And from there to R, I have this very nice map which takes any matrix A and takes its determinant. Is this map continuous?
Yes, so it'll be a polynomial.
Because it is a polynomial. No? You have a formula for this. By the way, the thing on the left hand side, I have written m n cross n r, but it really is also a vector space, right? What is the dimension of this vector space?
N square.
N square, right? So yeah, so it is really, so regarding it as just r to the n square, this is a continuous map. All right. Similarly, is continuous, then the map determinant inverse is going to be a continuous map from GLNR to R. Okay. So let's just say here mn cross n.
What is determinant inverse?
Sorry, it's just 1 by determinant. So I'll just write it like inverse, as in just inverse as a real number. So
yeah, so even if inverse of that determinant function exists, but might not be like, it's not a function. Maybe it does. R to GLN.
So let me just so this is 1 by det. Right. Yeah. absolutely. I should not be, the notation should be unambiguous. Is a vector space of dimension n square and GLNR is just those matrices A such that determinant of okay, what is GLNR? Surely this must have been defined in your linear algebra course, right?
Space of all vertical matrices.
Right. So this is the set of all invertible matrices, and you know that those are precisely the ones that have determinant non-zero. So the matrices that have determinant 0, by virtue of continuity of the determinant function, that is a closed set. So its complement, that is the matrices that have determinant non-zero, that's an open set. Okay, so this is one sentence. So the set of all square matrices is but one thing to sort of keep in mind is that whenever I say open or closed, there always has to be a topology, or there are at least, for us, a metric space. So here we are saying, well, I'm not really regarding these square matrices as linear maps. I'm just thinking of this as a vector space, and I'm taking the one of my usual favorite norms on this, which is either the max norm or the sum of absolute values. That is the p equal to 1 norm or the Euclidean norm. Okay. However, I do want to consider another norm in this on this space, which I'm going to define by the end of today's class, called the operator norm. Nonetheless, because of this marvelous fact that all norms on a finite dimensional vector space are equivalent to each other, continuity with respect to any one norm is the same as continuity with respect to any other norm. So let's try to get to that. Okay. So in order to do this, let's first do the following. We are talking about continuous functions. So this is maybe my last item. So special cases. So this number 7 was one long thing, right? Which sort of just gathered everything together. All the previous items, along with this algebra in R, that is 4 arithmetic operations. Now let's do the following. Any norm on Rn. So any norm on Rn is a continuous function, right? So I'm just going to write that. Any norm but what does this mean? So if you want to say continuity, then that means that I have to have metric on both the source and the target space, right? I mean, a topology more weakly, but we are dealing only with metric spaces. So when I say, so let's see how many different things are involved here. So I'm going to give a name to this norm, and let me not use the absolute value notation because you will see why. So let's call this norm something. Let's call this norm just let's just call this F, right? So what we want to say is that this function F from Rn to R but what does it mean that a function is continuous? Now, ignore for the moment that this is a norm. For a function to be continuous, it means that I have to have a metric on both the source and target vector space. Now, which is the metric that I'm going to use on Rn in order to check continuity. Okay, before that, which is the metric that I'm going to use on R? There is no mystery. It's just the usual absolute value, right? Just the absolute value of the difference. That's the metric that I'm going to use. But which metric am I going to use on Rn? And you see here, I have to be a bit careful because Rn now has a metric given to me, which is coming from F, right? However, I do not want to use that metric. The claim that I'm making is that this F is continuous with respect to the usual topology, right? Usual topology on R. Now, of course, what we are going to see is that the topology that is induced by the metric F, by the norm F is the same. But I cannot use that here because that's what I'm trying to prove, right? So it will be circular. So right now, I have to keep this, whatever is coming from the norm F at an arm's length. And I want to show that the function given by the norm is continuous with respect to the topology that I already have. With respect to and let's write this down. And let's write this down in terms of epsilon delta. So the norm on Rn, I'm going to denote like this, and the norm on R is just the absolute value. Okay, so what does it mean to say that this function is that a function is continuous? Okay. And now I'm going to do something a little bad. In the interest of time, I'm just going to sort of show this proof to you rather than fumbling our way through. See, at least sometimes fumbling our way through a proof is a better way to appreciate it. But here, let me just guide you. So in fact, what we are going to show is not just that the function f is continuous, but it is uniformly continuous. So what does that mean? Now, what do we have to show? You tell me. So what does uniform continuity of a map between metric spaces, of just a real valued map on a metric space, what does it mean? Or a non-linear space, what does it mean?
For all x greater than 0, for all epsilon greater than 0, there exists some delta such that x minus delta.
So for all epsilon greater than 0 and
for all x greater than 0. For all x belongs to the domain of interest.
Right.
There exists delta such that x minus a mod is less than delta implies that if x minus f.
Yeah, but what is a? A is an unbound variable here.
Okay. Yeah.
So where is a going to go? Are you going to say for all a and for all epsilon, etc.? You see, this is uniform. So that means that the delta does not really depend on
x.
Right. For any a, so really speaking, the role played by x and a is symmetric. So for all x and y, such that what happens?
Mod of x minus y is less than delta implies that fx minus fy mod is less than epsilon.
So x minus y less than
norm of that is less than.
Yeah, implies. So I want to put some notion of size. So the question is, which is f of x minus f of y is less than epsilon.
Yes.
Now, what is the norm on the right hand side? What is f and what is, so where is f of x? That's just a real number. So this is just an absolute.
So this is mod, and yeah, x minus y is the norm.
Right. And now you see,
Also, we can just fix any y. Oh no, okay.
Now, notice if I took the topology on Rn that was coming with respect to f, then I would have written f of x minus y less than delta implies this. But that's not what I'm going to do. I want this continuity with respect to the usual topology. So I'm taking a usual norm. Okay. So for p equal to 1, 2, or infinity, they're all right. They all give the same topology. So right now, let me not choose one of these. In fact, we will figure out which one is easiest for the calculation. You will see. But it doesn't really matter because the topology given is the same. All right. So this is what we have set up so far. Are there any questions until now? That this is what we want to prove. So claim. So this is the claim. So before we come to the proof, we have to first understand what the claim is. Is this okay? All right. So I'm taking it as there are no questions. Remember, if you have questions, you should absolutely stop me. Okay. So far, f is just a function, right? I have never really used anything about f being a norm. Right? So let us start using the fact that f is a norm. And here is the thing. So somehow I want to bound f of x minus f of y. So let's write down what f of x minus f of y is, right? And here is, so f of x is less than f of y plus f of x minus y. Is okay? From where?
Triangle inequality.
Right. And likewise, you can write f of y is less than or equal to f of x plus f of y minus x, right? Except, what about these two terms, f of x minus y and f of y minus x?
They are the same.
Because f is a norm, remember? So each one of the arguments is just one times the other. So what this is really telling you is that from the first one, I get f of x minus f of y is less than or equal to f of x minus y, right? But from the second one, you're also getting that f of y minus f of x is also less than the same thing. In other words, remember f is always taking non-negative values. So what we are saying is that this number on the left, f of x minus f of y, as well as its negative, is less than f of x minus y. That means the absolute value of that is less than x minus y. Okay, so far? All right. So the thing that I want to bound to be less than epsilon, I might as well bound f of x minus y. So let's examine f of x minus y. Right? So here, what is x minus y? So x is summation xi ei and y is summation yi ei. So ei is standard basis for Rn. So E1 is just 1, 0, 0, 0. E2 is 0, 1, 0, 0, etc. Okay. All right. So let us now take a look. So what is the vector x minus y? It is simply summation xi minus yi times ei. Let us write f. Let us take f of both sides. What gives now? What can I do on the right hand side? Remember, I want to bound this above, right? By means of some condition on x minus y. I want to bound this. So is there anything that I can do? I have f of a sum of vectors. So what do I get to say?
Maximum.
That is less than or equal to what?
Maximum of the value.
No, I'm not. I don't see how to get to a maximum, because you see f of a sum. I have f of a sum. Can I say anything about f of a sum?
Sorry, first is
Delta of EI, delta into EI.
This is because f is a norm, right? So by subadditivity or triangle inequality, if you will, right? Triangle inequality for the norm f. So what is this? This is summation of f of, okay, so let's not skip steps. F of xi minus yi times the vector ei, right? Okay. But now what is this? Remember, xi minus yi is just a scalar, it's just a real number. So by homogeneity, this just becomes the summation of what? Xi minus yi gets pulled out, but when it gets pulled out, what do I get? Xi minus yi. This is like saying the norm of 3 times v is 3 times the norm of v, right? That's what I'm doing over here. So this is xi minus yi times the norm of ei, the f norm of ei, except I have to do something. What do I have to do for xi minus yi?
Mod.
Mod. And mod just as real numbers. Okay. Okay. Now we're almost there. So okay, so let me just, homogeneity, how do you spell that? Let me just chicken out. F is homogeneous. All right. So now what I do is the following. So you see, this is beginning to be very nice, because look at this term xi minus yi, and I am summing all those absolute values over I. If I did not have the f of ei, then what is that? Summation over I of the coordinates xi minus yi, absolute value of that. Is that something to do with vectors x and y?
So we can just replace f of ei by like maximum of f of ei across all, and then it's just.
But that is true. But why do we want to do that? So here is the thing. Notice
because
summation I of xi minus yi. What is this?
Just the mod of xi minus yi, like the mod with 1, the standard.
So it is the norm of x minus y. Which norm?
The p equal 1 now.
Right. So this is the 1 norm. So you see, I'm in business over here. So in order to get to this, what I want to do is, I just want an upper bound, right? So let some m be the maximum of all the FEIs. So I'm taking the maximum over I. So the upshot is that I get upshot f of x minus f of y, absolute value, is less than or equal to f of x minus y. Remember, I had it up here, this one. And now in the next line, what did I get? That same f of x minus y, I have found to be less than or equal to what? I first replace each f of ei by something larger, namely m, and then I get to take m common outside, and m times x minus y. Okay, and I will just put 1 now. So let's go and make a choice over here. This is, again, I can take 2 or infinity after the fact, but this is the easiest, p equal to 1. Okay, so we are at the end now. Thus, what do I get? X minus y less than what will imply fx minus fy less than epsilon. Just look.
Epsilon by maximum m into n.
Epsilon by m. Just does the job. Okay. So good. We have shown that the norm is a continuous function. Very well. So let's sort of draw a line over this thing about continuity and prove that all norms on plane. On Rn equivalent. So this is enough to show that any norm f is equivalent to, and is equivalent to 1, right? One of the ones. See, all things are equivalent to each other is the same thing as saying pick one of them and show everything else is equivalent to that. So let's just do this. So what does it mean to show that this is the case? So we want to show that f of x for any x is between, and I don't recall, I think we used alpha and beta, correct? Alpha times the norm of x, and let's just call this, doesn't matter, and less than beta of x. Okay. Remember, this was the definition of equivalence. Now we are going to play a little bit of algebraic, simple algebra with this. Okay, so a couple of things. One, what I would like to do is I would like to just divide out by the norm of x. That is, so when I say norm of x, I will always mean the usual norm. If I mean the f norm, then I will say f. Right? Is this a valid step? Well, except for a minor caveat, right? I cannot divide by 0. But when will this result in a division by 0? When will the denominator be 0?
0.
When x is 0.
And only that, and only for that x, right? So what is the desired? So I have to check the desired inequality separately for x equal to 0. But but when x is equal to 0, what does the top inequality look like? Well, the usual norm is a norm and f is also a norm. So if x is equal to 0, then all the three terms are 0. So it's so there is nothing to check over there. So it is enough to check this for all x not equal to 0. Yeah. Okay. But now notice one thing. So just as a remark, note that f of x, norm of x. Remember, norm of x is just a scalar, right? And in fact, it's a positive scalar now. So this is really the same thing as f of x by norm of x. Yes? By homogeneity. So I'm going to call this f of u, where what is u? U is equal to, well, I said x divided by norm of x. But now just notice one thing. What is the norm of u? It's a very easy
Memory of
point.
one.
Yeah, so you see, if I take a vector and divide it by its length, just scale it by the reciprocal of its length, then I get a vector of length 1, no? Because remember, any scalar comes out of the norm. I mean, its absolute value. So the scalar here is the being that for which I'm using here is 1 divided by the norm of x. So this is just 1. So as a result of this, so from both of this, so remember, I want to show that this is the case. So it is enough this is just f of u for any of norm 1. That's what I have, no? This term here this term over here, I have shown that it really is equal to f of u. Where u has norm 1. So this is what I'm finally boiled down to showing. I need to show that if I take all unit vectors, so what are these unit vectors in Rn? If I have n equal to 2, then what are these vectors? Come on, we are like this close to it. So let's just. So when n is equal to 2, remember I have chosen the norm p equal to 1. So so which view am I talking about?
For the diamond.
Yeah, except not inside the diamond, but really on the boundary of that diamond, right? The actual thing that I draw. So I want to show that if f is any norm, then f evaluated on the vectors that have the p equal to 1 norm equal to 1, such a function is bounded above and below by, by positive constants. I should really have said that, for alpha beta greater than 0. Okay, so do we know anything that will allow us to show that the values of a function on a certain set are bounded above and below?
So beta we can also directly get from the previous idea we used for continuity.
Right. So let's just see this now. IE. Not IE, but let's just say. Oops. So, oops. The set U such that norm U equal to 1 is the unit sphere in Rn. By the way, over here, we did not really need to take p equal to 1 norm. We could have even taken p equal to 2, or anything is okay, really. Anything that we know is, that gives the usual topology. So it could be 1 norm, 2 norm, or infinity norm is the unit sphere in Rn. And I know that which is closed and bounded. So let's call this S. Therefore, f of S is compact in R. continuous image of a compact set is compact. Now, if I have a closed and bounded set in R, then you saw this last semester, correct? That if I have, maybe you saw this only for the closed interval, but really, if I have a closed and bounded set in R, then it will contain its largest and smallest, sorry, that came out wrong. Because the set is bounded, it has a least upper bound as well as a greatest lower bound. And because the set is closed, it will contain this supremum and infimum. F of S has largest element, let's say beta, smallest element alpha. So we are done, except are we?
We have to also say that alpha not equal to 0 because
correct. So why is alpha not equal to 0?
Because 0 vector is not in U. That's
so why is 0 not in? Why is 0 not? So 0 vector is not in U. That is true, and therefore the the real number 0 is also not in f of U, because remember f is a norm. In order for a norm of any vector to be 0, that vector, the only way is that vector is 0. But I am taking norms of only vectors that have unit length with respect to some other norm. But in particular, those vectors are non-zero, right? So f of that also has to be non-zero. Because f is a norm and 0 does not belong to S. Okay, so this proof is not very difficult, but it's a nifty proof, right? If it is not completely clear to you, if you're seeing this for the first time, then maybe you need to take a look at it until it sort of seeps in. Notice that many of the ideas that we have used, many of the ideas that we have defined, they were all used in a nice combination over here. We use norms, we use topology, we use continuity, and we use compactness. And we use the Heine-Borel theorem about characterizing compact sets in R. Okay, so it's sort of a nice capstone illustrating several of the ideas that we used. Now we are out of time, so we have to stop. I did not get to define the operator norm, but just to say something, that the operator norm is a norm that is on the space of all matrices of a fixed size. So a matrix, let's say an m by n matrix, if I take the space of all m by n matrices, then I will define something called an operator norm on that. Now you can say, well, but it's already a vector space of dimension m times n, so I have all of these norms already there. But this is going to be a different norm, right? Suited to the consideration that this matrix is not just a tuple of numbers, but it's actually this linear function between two vector spaces, both of which have their own norms, which we will typically take to be Euclidean norms. Right? So we will make this definition, but it will be helpful if you read that definition. Now, the nice thing is that in view of what we said is that, okay, we have this operator norm, but we have shown that all norms on a finite dimensional vector space are equivalent. So when it is suitable for us, we will do considerations with respect to, let's say, the infinity norm or one norm. As long as the considerations are of topology, that something converges or some set is open or not, or closed, it does not matter what norm I use, because all of them are equivalent. And we have now proved this. Also notice that in some sense, to show that the P norms for other values of P are norms, it is suddenly not so important to see. Because for our consideration, whatever norm, whether those are norms or not, whatever is a norm is equivalent. Now we have proved that. Okay. So please do try to read about the definition and basic properties of the operator norm, because now we are sort of entering the next part of this course, where we will, so far we did topology. We really discussed only continuity of functions, compactness, open sets, closed sets. Now we will really start doing calculus. In the next class, which is on Friday, I will define the derivative. And for that, we will need the operator norm. So please try to do some reading, and then we will embark on this sort of brave new phase. All right, exciting. Okay, so good. Let's stop for today.
Recording stopped.
Okay, so if there are any sort of quick questions, I can try to answer them.
Sir, so I read about this proof of norms on finite dimensional vector spaces are equivalent.
Right.
So in that proof, they're saying that since all finite dimensional vector spaces are isomorphic to some Rn, then like we don't have to prove it separately for that.
Okay.
So I do not understand that point.
Right. Okay. Okay. So let us try to run through this proof. Okay. So your point is that instead of saying all norms on Rn are equivalent, the question is, why does this show that all norms on any finite dimensional vector space are equivalent? That's your question, right?
Yes, sir.
Right. So let us say I want to change Rn to V. Okay. Oops, excuse me. Well, how will the proof go? So let us replace Rn by V. What will we do? So the initial part really stays the same. You see, I'm not using Rn anywhere here.
But you're choosing P equal to 1 norm, right?
I'm choosing P equal to 1 norm, but let us put it this way. I fix a bit. So you're absolutely right. Let us choose a basis for R. Let us choose a basis for my given vector space V. Let's call that basis E1 up to En. Okay. Now under this, so this will now define an isomorphism from V to Rn. And how? If I have any vector V, then I will write it as C1 E1 plus up to Cn En. And the bijection, the isomorphism between V and Rn is just that V is represented by the tuple of numbers C1, C2 up to Cn. Now, any statement that I make about V, I can make about Rn and vice versa by means of this dictionary. But I should qualify. By any statement, I mean any linear algebraic statement. That is a statement that involves only taking linear combinations, that is addition and scaling the vectors. It's an isomorphism of vector spaces, right? So it's a linear map. The assignment V going to the coefficient vector C1, C2 up to Cn is an isomorphism. It's really a dictionary. So if the coordinates of V are C1 up to Cn, and if coordinates of W are D1 up to Dn, then the coordinates of V plus W are C1 plus D1 up to Cn plus Dn, and so on, right? So to answer your objection, what is going to be this norm on V, the reference norm that I take? The norm of V is just C1 plus C2 up to Cn. I mean, absolute values of C1 plus absolute value of C2 plus up to Cn.
This is the L1 sort of norm there.
But that's exactly the P equal to 1 norm, no?
Yeah. Yeah.
Right. Okay. Now, so that settles what this double absolute value is. I just defined it for V. Now, if you look at the next part of the proof, or rather the previous part, the rest stays the same. But let's look at the earlier part, which said that any norm is continuous function. So you can say, well, instead of Rn, if I put V there, well, it's all right, because when I did this estimation, I looked at the vector x as summation xi ei, where I was thinking of x as really just a tuple x1 up to xn. But I think of e's as my given basis. And so the vector v will be represented by c1, c2 up to cn. And the exact same estimation will work.
However,
the point that I'm trying to make is that more than the nitty-gritties, the fact that two vector spaces are isomorphic means that any statement that you make about one vector space that refers only to the vector space structure of that entity is going to stay exactly the same when I translate it by means of a linear isomorphism.
but continuity aren't like only dependent upon the algebraic structure. It's also dependent upon the completeness of R, but other vector space might not have that property.
So for us, vector space means a real vector space.
Yeah, for real. Even in case of a real vector space, will the real vector space always be complete? Like R, like there will be subminimum for every upper bounded sequence. Something.
Now this is slightly confused. What does it mean to take an upper bound of a vector, of some set of vectors?
Yeah. So, like that's the notion of completeness in one dimension. In a higher dimension.
Well, there is the notion of completeness of a metric space.
Yes.
Right. But anyway, but in order to say Cauchy sequence, you have to have a norm, because you want to measure sizes, or at least you have to have a distance.
Yeah. So like similar to as you just defined according to that isomorphism, just find the
exactly. So you see, if I have a linear isomorphism with Rn, then whatever structure there is on Rn, I can simply transfer by means of this isomorphism to V. And vice versa. So if you want to show that all norms on any finite dimensional vector space V are equivalent, then I simply translate any norm in V will translate into a norm on R to the dimension of V, and vice versa. So any two norms, if I want to show them on equivalent on V, I can just translate them to norms on Rn. And it is equivalent to show, okay, this is terrible, I'm sorry. To show that two norms F and G on V are equivalent is equivalent to showing that the translated norms on Rn are equivalent. Just a dictionary. Notice that defining a norm on a vector space really only uses the structure of that set as a real vector space. That's all. It doesn't say what is the color of this element or something like that. Or it doesn't say, well, take it as a tuple and look at the first slot. No such thing is used. All right. So anything else? Anything else at all? You see, we are sort of at a, I don't know what to say, at an inflection point, or at a, at the, it's a sort of change of, it's a change of topic. So anything at all that you have, any question that at all that you have, it's a good time to ask. And if you do not want to ask it in open forum, you can write it in the chat for me.
So this norm thing, that we showed that any norm on Rn is a continuous function with respect to some other norm.
With respect to the one of the standard norms.
Yes.
Right? And the one that, okay, so, and the one that we used was
norm 1.
Was norm 1. But we also said that continuity with respect to that norm is the same as continuity with respect to the 2 norm or the infinity norm, because all 3 of them are equivalent to each other. So they define the same topology. Yes, but go ahead, please.
So I was just asking, is it trivial to show that it's continuous with respect to the F norm itself?
Okay, so good. It's good you asked that question. Let me give this as an exercise. All right. So you think about this, and the instinct is sort of correct. Let's do this not for a norm. Let's just do this for metric space. Okay. Exercises. So let X be a metric space. X is equal to a metric space. And let us say fix some A in X. So here is the first part. Consider the function from X to R, which takes any point X to the distance between A and X. What do you think about this function? It's the most natural function to consider, distance from a fixed point. Does it make sense to ask if this function is continuous?
Yes, it does.
Yes, because X is a metric space, R is. Now, imagine that X is a non-linear space. Then the question that you asked amounts to taking which value of A?
0.
0. Then distance between 0 and X is just the norm of X. And notice when I ask whether this function is continuous, you of course have to take the topology on X that is given by the metric on X. Right? So you see the question that you're asking is really this question. I'm just slightly generalizing it, but it's very tiny generalization. The argument is going to be the same, right? So is continuous. And I can really say with respect to what, but there is no choice here. X is a metric space. There is only one. There is only one topology. If I only say that X is a metric space, then there is only the topology coming from that metric. Okay. So, okay. So first, is it clear that the question that you're asking and the question that exercise that I'm writing here is still the same question, just slightly souped up?
Yes, it's
okay. So check this. This is absolute. This is true. It's not difficult, but you should do this as an exercise. But then there is a slightly more interesting thing. So here we left one of the points as fixed. What is the next interesting thing to ask? Let's not define this function. So let's now define. So let's call this. Okay. So let's define a function not from X to R, but from X cross X to R, which is X comma Y going to D of XY. But here you have to immediately be alert and ask me something. I'm claiming this function is continuous. But for a function, for it to make sense that for this function is continuous, what needs to happen? What needs to be there first?
A metric on x cross x.
Yeah, so there has to be at least a topology on x cross x, right? So we can say where open sets of x crosses are unions of, or let me not be so cavalier, unions of B, let us say U R cross P V S. Okay, so first, so I'll just say first what would you need to check? In order to be a topology, it has to be, the given collection has to be closed under arbitrary union and finite intersection. Is at least one of these obvious for the definition that I have given? Well, open sets, I'm saying, are arbitrary unions of ball cross ball. So if I take unions of an arbitrary union of an arbitrary such unions, then it is still going to be a union, right? So the union part is okay. What you have to check is that if I have two such unions and if I take their intersection, it is still a union of balls. By now we have done enough for you to anticipate something, that this proof is not going to be difficult, and all that it is going to involve is what? Hello.
The topological definition of continuity.
No. So we are even before that. I'm saying to check that what I have claimed, what I have asked you to take as the topology on x crosses x, to check that it is a topology, you have to show that intersection of two open sets is open. And all that it is going to involve is the triangle, is a basic use of triangle inequality. Because you have to show that if I just use distributivity, unions and intersections, they distribute, right? So what this amounts to showing is that if I take ball cross ball, intersection ball cross ball, such a thing is also a union of ball cross ball.
Sir, an intersection, right?
Yes. Notice intersection of ball cross. Okay. Anyway, so you see this is easy. First check that this is a topology. Then you also, is it induced by so those are side questions. But anyway, once you have a topology, then as one of you said, then to check that the distance function is continuous between x cross x and R is you just use the, you can just use the definition in terms of open sets to see that this works. Yeah, good. So that was a good spot to ask this natural question. That, but yes, indeed, the anticipation is correct. That it is much easier to show that the map from I mean, if I use the same metric, then it's easy to check that the map is continuous. The norm map is continuous with respect to the same norm. Okay, anything else? Very well. So let's stop for today, and then we will continue on Friday. Please do read about the operator norm. Review basics of linear operators if you need to. And because we are going to be needing both of those things. All right. Bye, everyone.
One second.
Yes.
Can we have a space where all the topologies are metrizable? Like there will be some metric that induces that topology. Is there a space of that sort?
No. So let me understand the question. Is there a space such that
any topology that can be defined on that will have metric? Okay, the trivial topology will never have a metric.
Yeah, right. So you see, that means that the only such space that will be a 1-point space.
Okay.
Right.
Okay. Thank you, sir. Yeah.
Right. But I sort of want to make a sort of general observation. See, a point set topology is such a subject is that generally speaking, okay, so don't quote me on this. Generally speaking, we already know the kind of topology that we want to study. And then we study that topology rather than saying, okay, here is a set, what all topologies can be there on it. But now I should hasten to add that it is certainly the case in various situations that the language of a topology is useful in very non-standard ways. Okay. Where you will see, yes, there are linear topologies, for example. There are non-standard topologies that do not come from our intuition in the Euclidean space. There are such topologies, many of them, and they're useful. But even in those cases, there is typically a reason why we want to consider that topology for some particular purpose, as opposed to saying that, okay, let's just look at all possible topologies. At least this is to the best of my knowledge. Okay, I could be wrong. That there is stuff that I do not know, but within my knowledge. As a, for just to contrast this, questions like, okay, let us study all possible. Let's consider what are all the possible groups, all possible finite groups, all possible simple groups, all possible groups of whatever description. Such a question, or let's try to classify all whatever mathematical objects of a certain kind. This is such questions can be of very deep interest. To the extent that I know, such a question about topological spaces, as far as I know, it does not really hold interest. But it could be my limitation. This is within my knowledge. Okay, good. So let's stop for today and we will continue on Friday.
Thank you, sir.
All right. Bye, everyone.